For much of the past year, astronomers around the world found themselves in an unusual and deeply frustrating position. They knew that one of the rarest objects humanity has ever discovered was moving through the inner solar system. Yet they were unable to observe it. 3I Atlas, only the third confirmed interstellar object ever detected, spent weeks hidden in plain sight, not because it vanished, but because the geometry of the solar system rendered it effectively invisible. From Earth's perspective, the object moved into alignment with the Sun, placing it behind an overwhelming wall of solar glare. This was not a technological failure or a lack of scientific effort. It was a fundamental limitation imposed by physics and orbital mechanics. Telescopes, no matter how powerful, cannot safely observe objects too close to the Sun's position in the sky. The glare overwhelms detectors, drowns faint signals and noise, and risks permanent damage to sensitive instruments. As a result, 3I Atlas entered a period of enforced observational silence. It was still there. Its orbit was known. Its trajectory was predicted with precision. Yet no new images, no spectra, and no direct measurements could be obtained. For scientists, this blackout was both expected and agonizing, because it occurred at exactly the moment when the object was undergoing its most important physical transformation. That transformation was perihelion, the point in the object's path where it passed. Closest to the Sun, on October 29, 2025. 3I Atlas reached this critical milestone at a distance of approximately 1.36 astronomical units, placing it between the orbits of Earth and Mars. Perihelion is not merely a marker on an orbital diagram. It is a stress test for any icy body, especially one arriving from interstellar space. The intense solar radiation near perihelion drives physical processes that reveal fundamental properties. Heat penetrates surface layers, volatile materials begin to sublimate, jets of gas and dust may erupt, and internal stresses can cause cracking, reshaping, or even fragmentation. The behavior of an object before, during, and after perihelion allows astronomers to infer its composition, internal structure, thermal history, and stability. In the case of 3I Atlas, these questions carry extraordinary weight because the object does not behave like a typical comet. Preliminary estimates suggest a diameter exceeding 5 kilometers, making it vastly larger and more massive than either Oumuamua or 2I Borisov. Its alignment near the ecliptic plane is statistically unusual. Its reported nickel-to-iron ratio appears extreme when compared to known cometary materials. These anomalies do not imply anything exotic by themselves, but they do demand careful investigation. Unfortunately, perihelion occurred while the object was observationally inaccessible, leaving scientists with models and predictions rather than direct evidence. Now, as early December 2025 arrives, that period of forced ignorance finally comes to an end. Earth's motion around the Sun gradually shifts our line of sight, and 3I Atlas is emerging from the Sun's glare into darker skies. This geometric transition marks the opening of one of the most scientifically valuable observation windows of the decade. For the first time since perihelion, telescopes across the globe can resume tracking the object. This is not simply a continuation of routine monitoring. It is the moment when theory meets reality. Predictions about brightness, evolution, jet activity, rotational behavior, and non-gravitational forces can now be tested against actual measurements. Post-perihelion observations are especially powerful because many physical effects persist even as solar heating begins to decrease. Thermal lag can cause activity to peak after perihelion rather than during it. Jets may reorient as rotation exposes new regions. Fragmentation may occur days or weeks later as internal stresses propagate inward. If 3I Atlas experienced significant changes near the Sun, those changes should now begin to reveal themselves. For months, scientists could only speculate. Did the object brighten dramatically during perihelion, indicating intense sublimation? Did it dim suddenly, suggesting fragmentation or surface collapse? Did jets intensify or shut down? Did its rotation rate change due to asymmetric outgassing? These questions remained unanswered, not because they were unimportant, but because observation was impossible. That uncertainty created a vacuum filled with hypotheses, debates, and caution. Responsible science does not draw conclusions without data, especially when dealing with rare and poorly understood phenomena. Now, that restraint is about to be rewarded. As 3I Atlas becomes visible again, astronomers are prepared to measure its light curve with precision, track any changes in brightness over time, and compare those measurements with models developed before perihelion. Deviations from expected behavior will be particularly significant. A smooth decline in brightness, consistent with increasing distance from the Sun, would support the interpretation of a large but otherwise natural comet. Sudden fluctuations, plateaus, or unexpected increases could indicate ongoing activity. Delayed sublimation or exposure of fresh material from beneath the surface. Equally important is the opportunity to study jet structure and orientation. Earlier observations suggested the presence of jets emerging from multiple locations, sometimes oriented in directions not obviously aligned with the Sun. For a typical comet, jets tend to point roughly away from the Sun as solar heating drives sublimation. Deviations from this pattern can result from rotation, complex topography, or localized volatile pockets. But persistent non-solar alignment raises deeper questions about internal structure. With improved visibility, astronomers can now attempt to resolve these features more clearly. Track how they evolve over time and determine whether they follow predictable rotational cycles or behave chaotically. Such measurements are critical for understanding whether the observed forces acting on the object are consistent with known physical processes. This observational window is also essential for assessing one of the most controversial aspects of 3I Atlas: the possibility of non-gravitational acceleration. Motion that cannot be fully explained by gravitational forces alone has been observed before, most notably in the case of Oumuamua. In that instance, the anomaly sparked intense debate over whether outgassing, radiation pressure, or more unconventional explanations were responsible. For 3I Atlas, the stakes are higher because of its much greater mass. Even a small anomalous acceleration would imply a substantial force. Post-perihelion observations are uniquely suited to isolating such effects because gravitational influences become more predictable as the object moves outward, while residual forces from outgassing or radiation can be more clearly identified. Detecting, measuring, or ruling out such acceleration will play a central role in determining whether 3I Atlas fits within existing models of interstellar comets or challenges them. In this sense, early December 2025 represents a turning point. The months of waiting were not wasted time, but a necessary pause imposed by celestial mechanics. Now, with the object re-emerging into view, astronomers have the chance to replace speculation with evidence. Whatever the outcome, the data collected during this window will reshape our understanding of interstellar visitors. 3I Atlas is not simply passing through our solar system. It is passing through a moment when humanity has the tools, coordination, and curiosity to learn from it. The universe has reopened the window, and this time, we are ready to look. As observational access to 3I Atlas is restored, the scientific focus shifts from anticipation to diagnosis. The period immediately following perihelion is often the most revealing phase in the life of a cometary body, because it exposes the consequences of intense solar heating rather than merely its immediate effects. When an icy object approaches the Sun, energy penetrates its surface layers, triggering sublimation of volatile materials such as water, ice, carbon dioxide, and carbon monoxide. Gas escaping from the surface can entrain dust, forming jets and coma that dramatically alter the object's appearance and dynamics. However, these processes do not always peak exactly at perihelion. Heat takes time to propagate into subsurface layers. and structural weaknesses may only manifest after internal stresses accumulate. This is why post-perihelion behavior is so valuable. It reveals whether the object's response to solar heating is smooth and predictable or delayed and complex. For 3I Atlas, this distinction is especially important because the object's estimated size places it far outside the norm of previously observed interstellar visitors. A body exceeding 5 kilometers in diameter possesses significant thermal inertia. Its interior warms slowly, and volatile reservoirs buried beneath the surface may become active only after perihelion. This raises the possibility that the most dramatic changes could occur weeks after closest approach rather than during it. Astronomers are therefore watching for signs of delayed activity, such as the sudden appearance of new jets, unexpected changes in brightness, or shifts in rotational behavior. Each of these signals carries information about the object's internal structure. A homogeneous, loosely bound body would likely respond differently to heating than a layered or compact one. Detecting these differences requires continuous monitoring, precise photometry, and careful comparison with physical models. By measuring how the object's brightness changes as a function of time and distance from the sun, scientists can infer the balance between reflected sunlight and emitted material. For a conventional comet, brightness typically decreases in a predictable manner as solar flux diminishes. Deviations from this pattern are significant. A sudden drop in brightness may indicate fragmentation, where the object breaks into smaller pieces that disperse and fade. A sustained or increasing brightness could suggest ongoing or newly initiated outgassing, perhaps from deeper layers exposed by thermal cracking. Because 3I Atlas was unobservable during perihelion, post-perihelion brightness measurements are the first opportunity to reconstruct what may have occurred during that critical phase. Jet morphology provides another crucial line of evidence. Jets are not random features. They reflect the distribution of volatile materials, the orientation of the object's rotation axis, and the geometry of solar illumination. Earlier, limited observations suggested that some jets from 3I Atlas were oriented in unexpected directions, not simply trailing away from the sun. This could be explained by a rapidly rotating nucleus, complex topography, or localized volatile pockets. But it could also point to a more unusual internal configuration. With improved visibility, astronomers can track the evolution of individual jets, determine whether they appear and disappear periodically, and measure their orientation relative to both the sun and the object's direction of motion. If jets consistently align with rotational cycles, this supports a natural explanation. If they remain misaligned or change unpredictably, the interpretation becomes more challenging. Perhaps the most closely scrutinized aspect of the post-perihelion phase is the search for non-gravitational acceleration. In simple terms, this refers to changes in the object's motion that cannot be explained solely by gravitational forces from the sun and planets. For most comets, non-gravitational acceleration arises from asymmetric outgassing, where jets produce a small but measurable thrust. The magnitude and direction of this acceleration typically correlate with observed activity. In the case of Oumuamua, an anomalous acceleration was detected without obvious signs of outgassing, leading to intense debate. For 3I Atlas, any detected non-gravitational acceleration would be particularly informative because of the object's mass. Even a weak acceleration would require a substantial force, which in turn would need a plausible physical mechanism. Post-perihelion conditions are ideal for isolating such effects. As the object moves away from the sun, gravitational influences become more stable and predictable, while residual outgassing or radiation pressure effects can be more clearly distinguished. Astronomers will use refined astrometry to track the object's trajectory with extreme precision, comparing observed positions with gravitational models. Any systematic deviation will be analyzed in conjunction with observed activity. If acceleration correlates with jet orientation and gas production rates, it strengthens the case for a conventional explanation. If acceleration persists without corresponding activity, it raises more difficult questions about the object's physical properties. Fragmentation is another phenomenon of intense interest. Many comets experience structural failure after perihelion as thermal stresses weaken their integrity. Fragmentation can range from subtle shedding of small pieces to catastrophic breakup into multiple large components. The pattern and timing of fragmentation provide insight into internal strength, porosity, and composition. For 3I Atlas, detecting fragments would be particularly valuable. A large, loosely bound object might shed material gradually, while a more compact or layered body might fracture in distinct events. Fragment detection is challenging because fragments are faint and rapidly disperse. But with coordinated observations from large telescopes and advanced image stacking techniques, even small pieces may be detectable. The presence or absence of fragments will help constrain models of the object's internal structure. Spectroscopy adds another layer of information. By analyzing the light emitted or absorbed by gases surrounding the object, scientists can identify specific elements and molecules. Earlier reports suggested an unusual Hamiltonian ratio in emissions associated with 3I Atlas. Post-perihelion spectroscopy can test whether this anomaly persists, changes, or disappears as different layers become active. For a natural body, composition is expected to be relatively consistent, though surface processing can alter apparent abundances. Significant changes in composition over time could indicate a layered structure with distinct chemical regions. Persistent anomalies would demand further investigation into the object's origin and formation environment. This phase of observation is not about proving extraordinary claims, but about exhausting ordinary explanations. Science advances by confronting anomalies with data, not by ignoring them or leaping to conclusions. The coming weeks represent a rare opportunity to apply that methodology to an object unlike any previously studied. 3I Atlas is large, fast-moving, and transient. Will not wait for us to be ready. The decisions made now about what to observe, how often, and with which instruments will determine how much we learn before the object fades into the outer solar system and eventually back into interstellar space. What happens after perihelion will either reinforce our understanding of interstellar comets or force us to expand it. Either outcome is valuable. What matters is that we measure carefully, analyze rigorously, and remain open to what the data reveal. As early December unfolds, the global astronomical community enters a phase of unprecedented coordination focused on a single transient target. 3I Atlas is now positioned where sustained multi-instrument observation is finally possible. And researchers are mobilizing resources accordingly. Ground-based observatories across multiple continents, space-based telescopes in Earth orbit, and even spacecraft around Mars are contributing data. This convergence is not driven by speculation or sensationalism, but by the recognition that opportunities like this are exceedingly rare. Interstellar objects pass through our solar system without regard for human schedules. And when one arrives with properties as unusual as those inferred for 3I Atlas, the window for study must be used to its fullest. This coordinated effort reflects a fundamental principle of modern science. No single instrument can provide all the answers. Photometric measurements track brightness changes over time. Spectroscopic observations reveal composition. High-resolution imaging probes structure and morphology. Astrometric tracking refines orbital parameters and detects subtle accelerations. When combined, these datasets allow researchers to test hypotheses with increasing confidence. Discrepancies between different measurements are not failures. They are clues. In the coming weeks, data will arrive rapidly and interpretations will evolve. Preliminary results will be published, debated, revised, and sometimes discarded. This process may appear chaotic from the outside, but it is the normal and healthy functioning of scientific inquiry. Public interest in 3I Atlas is also intensifying, as interstellar visitors naturally capture imagination. They are tangible reminders that our solar system is not isolated, but embedded in a dynamic galaxy where material from other stars occasionally passes through. However, the role of scientists is not to entertain speculation, but to provide clarity grounded in evidence. This requires discipline, patience, and a willingness to accept uncertainty. Several broad scenarios are possible, and each carries different implications. The simplest scenario is that 3I Atlas behaves post-perihelion, like a conventional comet scaled up in size. In this case, brightness declines smoothly. Jet activity weakens with decreasing solar heating. Non-gravitational acceleration aligns with outgassing models, and no unexpected fragmentation or compositional changes occur. Such an outcome would not diminish the object's importance. A large interstellar comet would still provide valuable information about the diversity of planetary systems and the processes that eject material into interstellar space. Another scenario is that some anomalies persist. Jets may continue to appear in unusual orientations, or brightness variations may not match simple models. These outcomes would suggest that our understanding of large interstellar bodies is incomplete. Perhaps 3I Atlas formed in an environment very different from our own solar system, leading to internal structures or compositions rarely encountered locally. Such a result would motivate revisions to models of comet formation, thermal evolution, and ejection mechanisms. It would also prompt re-examination of assumptions used to interpret earlier interstellar objects. A more challenging scenario involves persistent non-gravitational acceleration that cannot be fully explained by observed activity. In this case, scientists would need to carefully evaluate alternative mechanisms, including radiation pressure acting on unusual surface properties, delayed outgassing from deep reservoirs, or complex interactions between rotation and jet geometry. Extraordinary explanations are not the starting point of scientific analysis, but they remain part of the conceptual landscape once conventional mechanisms are thoroughly tested. The key is not to leap ahead of the data, but to let evidence guide interpretation. Fragmentation presents yet another possible outcome. If 3I Atlas breaks apart after perihelion, the nature of that breakup will be informative. Gradual shedding of small fragments would point to a weakly bound structure, while abrupt separation into large components would suggest internal stresses and heterogeneity. Fragment trajectories, brightness, and evolution would all contribute to understanding the object's physical makeup. Even the absence of fragmentation is meaningful, as it would imply significant structural integrity despite intense solar heating. Regardless of which scenario unfolds, the broader significance of this observation campaign lies in its methodological rigor. This is not an exercise in confirming preconceived narratives, but in confronting the unknown with careful measurement. The history of astronomy is filled with examples where anomalies initially dismissed as errors later led to major advances. It is equally filled with cases where unusual data were ultimately explained by improved understanding of natural processes. Distinguishing between these outcomes requires exactly the kind of sustained collaborative effort now underway. By early 2026, the observational window will begin to close as 3I Atlas recedes into the outer solar system. The object will grow fainter, its activity will diminish, and eventually it will become inaccessible once more. Before that happens, scientists aim to extract as much information as possible. The results will not arrive as a single definitive answer, but as a body of evidence gradually converging toward the most plausible interpretation. Papers will be written, challenged, and refined. Models will be updated. New questions will emerge. This is not a failure of science, but its strength. 3I Atlas reminds us that the universe does not conform to our expectations. It offers phenomena that test our models and occasionally exceed them. Our responsibility is not to force those phenomena into familiar categories, but to observe carefully, analyze honestly, and remain open to revision. Whether this object ultimately proves to be a conventional interstellar comet, an extreme natural outlier, or something that reshapes existing theories, its passage through our solar system is a rare opportunity. For a brief moment, material from another star system is close enough for us to study with unprecedented detail. The outcome will enrich our understanding of the galaxy, not because it confirms what we already know, but because it challenges us to know more.